Okie doke. Hello, everybody, and thank you for joining. My name is Raphael Motafort. I'm a senior researcher at NREL, and over the past year and a half, I've been working with the team to characterize the portfolio of wind energy software supported by the U.S. Department of Energy. As part of that work, we're hosting a series of workshops over a 2-week period, and today's is the third of 4, and it's focusing specifically on the wind farm analysis and wind farm controls groups of software. Some of my colleagues from NREL are co-hosting this workshop, and they're listed here. They're Pietro Bortolotti, Garrett Barter, Paul Fleming, Jen Stark, Misha Sinner, Rob Hammond, and Eric Simley. And just a heads up that this workshop is being recorded, and all of the materials, the slides and the recording, will be made available online within a couple of days. I'll go over the agenda here quickly just because it's changed since the workshop was initially planned. I'll start with this intro, and then I'll give an overview of the WETO stack as a whole. And I know there's a large portion of attendees that have also attended previous workshops, so this is more or less the same thing from the earlier ones, so thanks for your patience in just hearing the same thing again. Then there will be an opportunity for open discussion specifically related to this overall collection of software that we call the WETO stack. And then after that, the model owners from FLORIS, FLASC, OpenOA, and Hercules will give an overview of their tools, and the presentations are generally structured as an overview of the models and methods, a concrete introduction to the software, so it's typically a quick demo of how to run it, and then an overview of their future roadmap. And then finally, there's another opportunity for community discussion based on focusing specifically on the 4 software that we're talking about today. And I just wanted to point out that we're excited for this workshop and the opportunity to have this 2-way communication between the model owners and you, the community of users. So that's why we've allocated such a large portion of the time for open discussion. As I see it, these parts are really key to the workshop. We want to hear your feedback on the WETO stack and how it can be improved, what's working, what isn't, and ultimately how these tools can have the greatest impact in supporting wind energy. So before getting into the WETO stack overview, I want to just give a quick introduction to the Holistic Modeling Project, which is the project at NREL that has supported these workshops and the coordination effort. The primary funding mechanism for wind energy research in the US is through the US Department of Energy, and specifically the Wind Energy Technologies Office, or WETO. So that's the WETO in WETO stack. And WETO's mission is copied here on the left, and it's a little long, so I'll just summarize it in that WETO invests in wind energy research, development, demonstration, and deployment activities that enable and accelerate the innovations needed to advance wind energy. And in 2024, research, development, demonstration, and deployment nearly always involve some sort of modeling or analysis software, and quite often require new software development. So you maybe can rephrase this as WETO invests in wind energy software that enables and accelerates the innovations needed to advance wind energy. The scale of wind energy research supported by WETO is quite large. I'm showing here on the right a list of all of the active projects only at NREL, funded by WETO. And the purpose here is just to show the breadth of active projects. That there's a lot going on, and many of these projects support or use the software that we're talking about here in the WETO stack. And like I said, this is just the NREL projects, but I'll also point out that many national labs contribute to the WETO stack, and including the ones that are listed here on the bottom. The portfolio coordination task of the Holistic Modeling Project is working on addressing this issue that comes up where we have so much software being produced, where there's kind of a loose, all these software tools exist as kind of a loose collection of software. So we're trying to go from this paradigm of this loose collection of software in the past to a future where there's a more cohesive, better coordinated software stack. So that's what we're in the process of doing. It's a 3-year project. We just finished the first year, and it was primarily around getting data in place and engaging with model owners. The current year involves using some of the methods we developed last year as well as engaging with the user community, and that's exactly what these workshops are. And then the final year will involve additional portfolio streamlining and putting a coordinated roadmap into place. So I hope that sets a bit of context, and now I'll describe the WETO software stack as a whole. You may have seen this image. It's on the WETO Stack website. This is a map of the software projects grouped by what they do. For the sake of this workshop, we've deviated slightly from this grouping. Instead, we've planned these workshops by the technical area in which the software are used. And to stay in line with these workshops, this is how I'll describe them here. So just to set the stage for the next few slides, I want to describe these groupings at a high level. We'll start with the TEA and cost models. This group of software allows for estimating the capital costs and operating costs to ultimately determine whether and how to develop a wind energy project. So these are often used early in the life cycle of a wind farm development. Then there's the software for wind farm controls and analysis, and that's exactly what we're talking about today. And these allow for doing generally a low fidelity estimate of energy production. So after a first sanity check with the TEA and cost models, you might use the wind farm controls and analysis models to start working on a schematic design of a wind farm and how it'll integrate into the grid. Next, there are the mid-fidelity tools for wind turbine and wind farm analysis, and these are all lumped into the OpenFLASC category. And with these, you can do a more detailed design of a wind turbine and wind farm. And then the systems engineering tools are a group of optimization-oriented tools, and these work closely with OpenFLASC to do whole system optimizations of wind turbines. And then finally, there are the high-fidelity modeling tools that allow for researching any kind of research or technical area that you need the sort of high fidelity, like a novel blade treatment or any kind of advanced wind farm controls. So now I'll move into describing the tools within the sections themselves. These are the systems engineering tools. I borrowed this graphic from the Big Adaptive Rotor, or the BAR project, and I thought it was an especially nice diagram to show how each of these tools relate to each other in a real workflow. WISE is modeled here or shown here in this light yellow, and it's a powerful design optimization tool. It has a lot of capability, but its core intent is to enable the controls co-design of wind turbines. So that's the coupled optimization of the software and the hardware of a wind energy system. WISE integrates Wisdom into its design loop, and Wisdom is another optimization tool with lower fidelity models tailored to systems engineering. WISE also couples Wisdom to OpenFLASC and Rosco, which are two other tools in the WETO software stack. And then you can add PyNUMAD to this loop for a higher fidelity detailed design of the composite structural model of a rotor. WindSE is kind of shown here on the bottom right. It's not yet integrated into this design loop or this workflow. It's a RANS CFD model designed specifically to strike the balance between engineering scale models and flow resolved CFD. And it's specifically tailored to optimization problems. So that's kind of the context in which it lives. The TEA and cost models are used or can be similarly mapped. And I'll start describing this kind of here at the right, on the right side with WAVES. WAVES is a software that models capital costs, operating costs, and energy yield to determine the total asset value. It gets its CapEx estimate from either Land Bossy, Hybrid Bossy, or Orbit, which calculate the balance of system costs for land, hybrid, or offshore wind power plants, respectively. And Coral is kind of an add-on to Orbit that enables modeling the cost impacts of shared balance of system infrastructure. So things like shared ports, shared roads, that sort of thing. WAVES gets the OpEx estimate from Wombat, and it uses FLORIS, which we'll talk about today, to estimate energy yield. And then Narwhal on the top right is a library of cost equations for offshore wind farms. It integrates some of these other tools, but it isn't kind of packaged into this the same workflow here. The next collection of software are the wind farm analysis and controls models, and these are mostly related to characterizing and improving the energy yield of a wind farm. And these are the topic of the rest of the workshop, so I'll skip through them, but I just wanted to kind of point out that they're also a whole grouping within the WETO stack. The OpenFLASC collection of tools are, of course, OpenFLASC, along with a set of adjacent tools that enable using OpenFLASC effectively. OpenFAST itself is a multi-physics, multi-fidelity whole turbine simulator for the coupled dynamic response of wind turbines. The OpenFAST software contains distinct modules for aerodynamics, hydrodynamics, control and servodynamics, and structural dynamics. It also supports modeling a variety of wind turbine architectures, including floating offshore wind turbines. And then there's FastFarm. FastFarm is a superset of OpenFAST that contains additional modules to enable full farm modeling, including wind turbine wake interactions. And what I'm showing here, I should describe these figures quick. You may have seen this one from OpenFAST. This is from the OpenFAST documentation and kind of describes how the physics modules fit together. And then on the right, FastFarm has its own additional modules for modeling the full farm, but it has OpenFAST right in the middle. So it has multiple instances of OpenFAST to model the turbines, and then some additional modules to model the aerodynamics of the wind farm. OpenFAST includes a basic wind turbine controller, but the Roscoe package, which is the reference open source controller, is a full-featured baseline controller, and it includes a generic tuning process for wind turbine models. So that fits into the OpenFAST system just here on the top, as it can plug directly in as the wind turbine controller. And finally, just to note it here on the right, is the OpenFAST toolbox. It's a Python package that has a large number of utility functions for working with OpenFAST and FastFarm. It's essentially a collection of pre- and post-processing tools that have been useful to NREL researchers. So we've been collecting them here and making them useful, making them available to you. The last grouping of tools are the high fidelity models. These tools are all CFD, addressing specific components of the wind energy simulation cascade of scales. At the largest scale is ERF, and that's here on the left. ERF is the energy research and forecasting model. It's an atmospheric model that couples the mesoscale to the microscale, and it's capable of simulating regional scale weather, and the target domain size is between 10 and 1,000 kilometers. ERF couples to AMR wind, which is a model for the atmospheric boundary layer, and its target domain size is less than 10 kilometers. AMR wind can use the regional weather model from ERF as a boundary condition or forcing function for its own simulation. So those two are coupled that way. And then AMR wind can couple to NALU wind to do a fully blade resolved simulation. And the target domain size for NALU wind is less than 1 kilometer. AMR wind and NALU wind together are referred to as ExaWind, owing to their development within the Exascale Computing Project. And all of these software are GPU compatible and support workstation and HPC use. A relatively new project that isn't listed here is called OpenTurbine, and it's a structural model specifically designed for integration with ExaWind. It's in active development for the next couple of years, and more information will be given at the HFM workshop. And by the way, I'll just point out the HFM workshop was previously scheduled to happen this week, but due to scheduling conflicts, we had to postpone it, and we're shooting to do that toward the end of the summer. Okay, thanks for bearing with me for that overview of the WETO software stack. And now we can move into just an open discussion on this from this perspective, high-level WETO software stack. But before we start that, I've got some poll questions that I'd like for you all to take part in. Okay, you should see them on your screen now.
Somehow the poll is not working for me.
Yeah, same.
Oh, it is not showing up, or it doesn't move.
Something in the chat?
It did work for me.
Yeah, it's also working for me.
And
Okay.
yeah, there's responses coming in. It should be a pop-up, Paul. Do you see a pop-up?
There's a button that says view poll, and then it says there was a problem reaching this app. Maybe I'll restart Teams. Yeah, Bart, that's what I'm also seeing.
I'm having the same problem,
Ah,
but I do see people responding, so.
interesting. Well,
I wonder if it's an NREL problem. Because I got the same thing. I had issues opening Teams at all today, so.
I don't know. And try to post the questions.
Raf, is there a text link? Maybe post a text link in the chat separately.
It's all done through Teams, so
Oh,
there's
okay.
not, unfortunately, there's not a text link. Yeah, that is too bad.
We can wait.
Yeah. Yeah, I'll just wait. Okay, I think the responses have more or less slowed down. So yeah, sorry about that, and thanks for those who did respond. Share my screen again. Okay, yeah, so yeah, thanks for those who did respond. Sorry for the technical problems. Generally, what we were trying to get from the polls are an understanding of where the familiarity with these group of tools and kind of how, to what degree you're interested in integrating other sets of tools or coupling other sets of tools with the wind farm controls and analysis tools. So to anybody who did respond, if you have anything to share in that area, we'd like to hear it. And also, we have some discussion topics here. So regarding the WETO stack as a whole, what's missing? What, especially those who have heard this talk, this intro a few times now. Yeah, what do you think is missing in as far as the capabilities or the explanation of it? And where have been your challenges in using the WETO stack? If you raise your hand, we'll call your name to ask a question.
Go ahead, Pete.
So my main confusion, I guess, with the whole stack has been, what do I choose for a given scenario? So my particular thing that I care about is like unsteady modeling of wake steering, for example. So I see Fast Farm could potentially help me there. Wind SE, potentially the very high fidelity, the LES stuff, but I probably don't want to get into that because I'm doing engineering work right now. So I don't know. Do you have any advice for that sort of decision?
So that specifically, yeah, I think Fast Farm is for a high fidelity tool or higher fidelity tool than FLORIS, then yeah, that's what we've looked at as well. I think that's kind of where Fast Farm sits. But as far as making that decision more generally, I think it's a good point that, as I understand it, you're trying to understand how to navigate the varying fidelities in the models to maybe answer a slightly different question than where you're at now. So if you're doing some sort of farm level control design, you want to take the next step. How do you navigate something like this map of models to pinpoint what you need to do or what you can use? Yeah,
that sounds about
that,
right. Like an index of everything, or a roadmap. Where do I enter the ecosystem?
Yeah. Generally, that's a good point, and I don't think we have something like that just yet. That's kind of what I'm trying to go for with these few slides, but I think we need that one level in the hierarchy up. So some mapping instead of words here. I think we need some sort of mapping is what it sounds like. Would you say that's accurate?
Yeah, I think that would be helpful.
Okay.
Thanks.
Yeah, thanks for the feedback. I appreciate that. All right, if there's any other questions, bring them up now. Otherwise, we can move on to the next section. Great. Well, yeah, thanks, Pete. Appreciate that. And Misha, you'll have to, yeah, it seems like Teams is maybe not working out today. So you'll have to just share your screen directly instead of passing control.
Okay. If you actually, because I can still see that I can take control. So if you
Oh, okay.
if you share that, I might just be able to take control of your, like the one being coming from your, I don't know. If you want to like just go into presenter view and I can just try taking control and see if that works.
Sure.
Did you just get a request to like give me control?
Yep, you got it.
All right, let's see if I mean, let's see. Yeah, okay. I think it's gonna work. Sorry if it's a bit laggy for anyone. What happened there?
There we go.
Okay, you can advance it as well, maybe. I don't know. All right. Yeah, so hi everyone, I'm Misha. I am part of the wind farm controls group here at NREL, and I'll be talking about FLORIS, which is our low fidelity or sort of analytic engineering wake model for wind turbine wakes. So just to call out that there's a pretty large group of people actively working on the wind farm controls software stack here at NREL. This is a snapshot of kind of a handful of the people who are currently working on it, but there are people who have worked on it before, and there are also lots of external collaborators and developers, which we really appreciate. So yeah, this is by no means a comprehensive list, and I'm not going to name everyone, but here's a few faces you might see around. So yeah, FLORIS is our engineering wake model for looking at wake interactions within a wind farm, particularly when you have multiple turbines and turbines operating in each other's wakes. It's a collection of wake models, turbine models, which are modeled as actuated disks, a kind of a set of tools for handling how you want to run your inflows to the wake model, and a set of design tools for optimizing your wind plant's performance given the wakes within the wind farm. So the wake models, I should mention FLORIS, the S is for steady state. So it's a steady state wake model, no dynamics included, but just show the time averaged or the sort of steady state behavior of wakes within a wind farm. That allows us to implement very simple analytical models that can be solved very quickly. So you can run hundreds of thousands of wake model situation calculations in a second. And we have a kind of a library of different wake models that have been proposed in the literature and that we use in-house here, that I won't go through in detail, but just to say that there's many different characterizations of the wakes which have different strengths and weaknesses in terms of modeling real situations. Turbines are modeled as actuator disks, so essentially a power and a thrust curve as a function of wind speed. But we've recently released FLORIS 4.0, and in FLORIS 4, we've kind of greatly expanded our capabilities for turbine modeling so that we can model different types of operations. So yaw misalignment, which was already available in previous versions of FLORIS, but now also turbine derating, peak shaving, the change to the power and thrust coefficients due to things like active wake mixing, shut off and curtailment and many other sort of things like that we're now in development for. But yeah, just sort of we've opened the door for much more sort of advanced operation modeling of turbines now with FLORIS 4. Also in FLORIS 4, we've expanded our handling for how inflows are handled. So basically with FLORIS, we vectorize the flows, the sort of input conditions that you want to run the farm at and solve them all essentially in parallel in a vector operation. This allows us to run many calculations quickly and get answers quickly with FLORIS. But we have handling for specifying your inflows as a windrows, as a series of inputs that you want to run, kind of as though you had, maybe you gotten them from a time series measurement. We can handle heterogeneity in the inflow, and we're also building out capability for reading in inflow data from common formats such as WRG files and other kind of formats that you might see out there for handling wind data. And finally, I'll mention also our design tools. So these are sort of centered around two main optimization routines. One for optimizing the yaw angles of a wind of the wind turbines within a wind farm to find optimal yaw angles that steer the wakes away from downstream turbines and maximize power capture across the entire farm. And layout optimization, which moves the turbines within boundaries and within the wind farm boundary to again mitigate wakes given the windrows and the frequency of different wind direction and wind speed conditions. So what does this actually look like? Here is sort of a pretty minimal FLORIS run script. So maybe, well, let's see, 30 lines of code, but only maybe 10 of those are actually code in order to load up a FLORIS model, which is this line here. This is to bring in your specified input file and assign that to an object, the F model. Then a few lines to specify an inflow condition. This is using the time series data handling object, but essentially here I'm randomly assigning 100 wind directions, wind speeds, and turbulence intensities to go in sort of a pairwise calculation. So there are 100 conditions to run. Next line just sets that time series object onto the FLORIS model to be, to prepare to run. And then the run call, this is the one that does the work, the one that actually computes all the wakes and the effective velocities at each turbine. And then a couple of lines to extract the outputs that we might be interested. So turbine and farm powers in this case. So again, it's relatively simple to set up this Python script and run a simple calculation with FLORIS. And this, I haven't exactly timed this script, but this will run in less than a second for these 100 conditions on my laptop. So going a little bit into what that input file looks like. It's a YAML file, so it sort of mirrors a Python dictionary. And essentially what we have here is, to start the file, a few kind of sort of boilerplate parts on logging and sort of documentation. Then a specification of the grid points, which is how you want to how much you want to resolve the sort of the velocities at the wind turbine rotor. Probably, again, not something that you likely need to change, but can be changed. The farm details, this is where you might want to implement your own farm. So specifies the layout in X and Y of the wind farm. But I want to point out here that these can also be dynamically set within the script. So although you can specify this or any of the other parameters within the input file, you can also dynamically set these within your run script. So that's another way of doing it, and that's often how we actually end up doing it. Similarly, inflow details. Again, here you could specify all the inflow conditions that you want to within this input file. More often, we will specify those in the run script and then set them before we run the calculation. And then this is where you'll select your wake model from the library of wake models that we have. And finally, on the right-hand side, which is just an extension of the same script, it just didn't fit very nicely on one slide, are all the sort of parameters for each wake model. And so this is, if you want to fine tune the results that you're seeing, this is where you'll set the parameters of the wake model to adjust how that's calculating the velocities in the flow. And the second type of input file that you'll need is a wind turbine input file. So this specifies the power and thrust curve of the wind turbine essentially, but also a few other sort of physical parameters such as the hub height, rotor diameter, and also selects how you want the turbine to operate. So how you want to model, for instance, the loss in power due to yaw or other aspects of the operation of the turbine. Okay, so for those who have seen FLORIS before and kind of maybe that was all a little bit of things you'd seen before, here's something new. This is now released in FLORIS 4.1. This is a optimization, a layout optimization that we do by randomly searching the domain. This is maybe not as efficient as gradient-based optimization, but allows us to handle complexities like disparate boundary conditions, or sorry, disparate boundaries with maybe shipping channels between them that make it difficult for gradient-based solvers to kind of handle. And basically, what we do here is we perturb turbines randomly. We check whether they still satisfy constraints, so they're still within bounds and they still satisfy minimum distance constraints. If they do, we check whether they improve AEP. And if they do improve AEP as well, then we set that as the new sort of, candidate optimum and can continue our search. To speed this up and let this run quickly, we also run this in, we also have some handling for sort of a genetic algorithm, so we can run this in parallel. And the idea with this is that it's very robust to complex conditions, robust to the initial condition that you lay out the turbines with. And so you can kind of quickly, or at least reasonably quickly get a semi or a close to optimal layout without having to think too hard about kind of fine-tuning gradient-based parameters and things like that. So yeah, again, that's in the very recently released FLORIS 4.1, so you can find that. And there's examples there too. Okay, so this workshop shouldn't be the end of your discussion with us on FLORIS. There are many ways to kind of be involved with FLORIS. First of all, we've made a big effort to put good doc strings all throughout FLORIS. So you'll find, a description of what each function does, at least at the sort of top level for, the kind of user interface. But also a pretty rich set of examples on the GitHub repository. There's, sort of 10 basic examples-ish, and then, I don't know, 30 or 40 sort of more in-depth examples on there. So do take a good look through the examples. We have also made an effort with our GitHub pages documentation. And finally, we have, to be a bit more interactive, we also have GitHub discussions and issues pages that we respond to as promptly as we can. So if you have questions and you want to reach out, please feel free to do so on GitHub discussions and issues.
Sorry. Hey, we're both doing it. Hey, Misha, we should post these roadmaps in the chat because we have run out of time.
Oh, my bad. Okay. Yeah. Yeah. We'll leave it there. Thanks. Yeah. Sorry about that.
Okay. All right, Paul, would you rather share the screen yourself or do the same, take control like Misha did?
I'll try taking control.
Yeah.
Okay, I think. Yeah. Okay. Hi, everyone. I'm Paul Fleming, one of the principal investigators for wind energy control systems at NREL, and I'll be talking about FLASC. FLASC is our software framework for, excuse me, 1 second. Comparisons of SCADA data between engineering models like FLORIS, or specifically FLORIS. And it started really as our in-house code set for analyzing campaigns of wake steering or other types of like uplift analysis, but is really expanded into a comprehensive tool suite when you're working with engineering models and SCADA data at the same time to help make these comparisons. It also uses the engineering models to facilitate certain types of filterings and bias corrections. And to finally, more recently, it includes model fitting for those engineering models based on SCADA data. So I'll come into that now. So like I said, one important package of tools in FLASC is SCADA filtering. So these include filtering for abnormal conditions, stuck sensors. We also include power curve filtering and things like that. Secondly is bias correction. Like I mentioned, we'll get into this more in the later slides, but using engineering models to help identify steady biases and signals like wind direction measurements. Uplift analysis, trying to look at, compare engineering models and SCADA data when you're running a type of toggle test and trying to see the benefit of a certain controller application. And then finally, model fitting. So using SCADA data to calibrate engineering models in FLORIS. So FLASC includes really two sets of examples when you download it. One is based on artificially generated data, and a second set uses the SmartEL wake steering field campaign. So this is a data set made public by NG and NG Green, I'm sorry, and is the data set that comes from this paper, which was a test of wake steering and an NG site collaboration between NREL and NG in the SmartEL campaign. And the examples sort of work through accessing and cleaning the data, preparing a FLORIS model of the site, downloading the data from the Zenodo location where they're available for free, setting it up in FLASC structures. Then it goes through the analysis of the data in a way that matches what was done in that paper. So you can see how we produce those analysis results. And then finally, some new things, model tuning of engineering models to the data sets. And so to demonstrate FLASC in this meeting, I was going to go through this set of examples quickly to show some of the usage of FLASC and some of the capabilities. So the first examples are about preparing the FLORIS models. So FLASC makes a lot of use of FLORIS. And here you can see the site is a 7-turbine farm where one of the turbines is implementing wake steering for the benefit of one other turbine. And then we have a number of sort of available reference turbine options that can be free stream or waked depending on the direction. Here's the FLORIS model constructed for the site. Secondly, there's, like I said, examples for downloading the data and then setting it up. FLASC uses a pandas data frame as one of its main structures for holding data, and it assembles things or it expects you to assemble the data into a kind of set frame. So the script goes through the process of downloading the data and then converting the data from sort of arbitrary names of channels to the ones that FLASC will be expecting. So after you do this download and cleaning, you get a data frame that looks like this, where the turbines are 0 indexed and they have these standard names. So like POW, this is the power of the first turbine. You see a wind speed, different expected channels that it can work with. It uses NANs to indicate missing or faulty data, and then UTC timestamps. Once the data is in this structure, then everything else becomes pretty easy to run once you have it kind of conditioned like this. So for example, estimating bias. This code shows the process of estimating the bias of a turbine in this data set. And FLASC provides tools using FLORIS, for example, to identify turbines that are in the free stream for given wind directions. It can set a reference wind direction. In this case, we're going to use the turbine we're trying to calibrate the bias against. Here we're going to set the reference wind speed and reference power by accessing a function that makes a set of turbines that are free stream for a given direction and within a certain radius of the turbine that we're interested in. So like this, we get a set of wind speed, wind direction, and power references for our calculations. Now we can call these bias estimation functions that can make a comparison of the wake profiles we're seeing in the SCADA data to FLORIS. And like this, FLASC can identify steady biases in the wind direction measurements of each turbine if you sort of go through and do this process for each of them. And that gives a common use case for FLASC. From there, we can look at analyzing what we call the energy ratios. So the ratio of energy produced by a given turbine relative to an unwake turbine. So here we're going to split the data into a baseline and controlled set based on one of the columns that indicates the status of the toggle. Then we build an energy ratio input item where we label these two sets. We'll call one baseline and controlled and assign some colors. And then we can use the energy ratio functions in FLASC to compute the energy ratio given the defined reference power, wind direction, and wind speed, and then make plots like this. So this plot is showing, just for SCADA data, the energy ratio of the downstream turbine in the case where the baseline control is applied upstream or the controlled turbine. And so you see that the energy ratios are similar, except in this part of the wake where we're applying wake steering, and there we see an uplift in energy production of the downstream turbine. We also provide some histogram of amount of data per wind direction, and then some indication of the distribution of wind speeds within each wind bin. Uplift calculation is just a small change in how we analyze the same data. So it uses the same structures that we already set up, but now we're going to ask to plot the uplift from baseline to controlled. We're going to call this uplift. And here, instead of just doing the energy ratio once, we're telling it to use a block bootstrapping of 40 times. So resampling the data 40 times according to time blocks in order that we can produce these sorts of uncertainty bands around the analysis. Here we're selecting the sort of default 90% confidence intervals. We can also make comparisons with FLORIS using these same methods by regenerating the data in FLORIS from the SCADA data. So supplying the reference wind speeds and directions, and then calculating the expected power of each turbine with FLORIS. We can produce matching data frames that can then go through the same process. And now we'll build an energy ratio input that includes both the baseline and controlled SCADA data, but also the baseline and FLORIS data, baseline and controlled FLORIS data. And now we can make energy ratios of all these things together. So the baseline and controlled SCADA data, baseline and controlled FLORIS. And finally, we have some methods for computing the total uplift over a given region. So you specify the region and you ask for like a single number instead of a visualization of calculated uplift. Also, you can specify number of bootstraps to do to calculate uncertainty intervals over that uplift. And so in this case, we would get an output like this. Calculated percentage gain over these regions from the SCADA data and from FLORIS. And we could have also put some uncertainty bands in these printouts. So FLASC is a bit younger than FLORIS, so a lot of these things are a little bit not as completely robust as FLORIS, but in general, we try to follow the same WETO software best practices that Raphael has put together. So we use sort of normal Python doc strings within the code as one place to kind of learn the code. We try to follow this best practice. Secondly, like I said, we ship with two sets of examples. One set related to artificially generated data to kind of make particular points, and then this set of examples using real data. We have online documentation from GitHub pages built into the repository. And finally, like FLORIS, we have at the GitHub page, we have places for questions and answers in the discussions. Coming up for FLASC, a few exciting things. So really focused on expanding the model fitting capabilities, implementing further assessments for power and energy differences, our own, and also linking to some external toolboxes for these purposes, and continuing to build out the API and the documentation. Okay, thank you.
All right. You're up, Eric. This is
Okay.
OpenOA.
Great, thank you. I'm Eric Simile, and I'll be talking about OpenOA, which stands for Open Operational Assessment. And this is software for assessing the performance of wind plants using operational data. Rob Hammond is the main software engineer on this project and is also on the call. And then there's a much larger team that's worked on this software since it was created in 2018. So this is a little different than the other tools today because it does not have a controls focus, really just looks at general wind plant performance. So OpenOA is built around this plant data and plant metadata classes for organizing and storing operational data. So it contains categories, different data categories like asset information for the turbines and met towers in a wind farm, the energy production for the wind plant at the revenue meter, curtailment and availability losses, turbine level SCADA data, met tower data, and then reanalysis wind resource data sets like MERA2 or the ERA5 data set. And then there are lower level utilities toolkits. And these include things like filtering data, power curve fitting. There's a toolkit for downloading reanalysis data that many of the analysis methods use in OpenOA. And the utilities toolkits can be used as standalone toolkits. They just, can operate on Pandas data frames. They're also the building blocks of the main analysis or operational assessment methods in OpenOA. So these OA methods, first there's AEP analysis. This estimates the long-term annual energy production of a wind plant based on a few years of data. Turbine ideal energy, which estimates how much energy the wind plant could produce if all turbines were operating normally all the time. We can have a method for estimating electrical losses within a wind plant, performing a gap analysis, which I'll talk about next. And then the past few years, we added some new capabilities, estimating the total wake losses in a wind plant using SCADA data, and then detecting static yaw misalignment on individual turbines, although that's a very basic method that is just a starting point. The code comes with documented examples in Jupyter notebooks that walk through creating a plant data object and running all these operational assessment methods. And it uses open data from an NG wind plant in France that has 4 wind turbines. All right. So the objective of the software is to was really to benchmark pre-construction estimates of energy yield. So calculating the long-term expected AEP, annual energy production of a wind plant based on operational data, and then comparing that to pre-construction estimates of AEP. But in addition to just benchmarking those pre-construction AEP estimates, we also want to know what's causing gaps between the pre-construction estimates and the observed AEP. So that's what we call a gap analysis. And ideally, we'd want to understand for each of these steps that determines energy production of a wind plant, is it being over-predicted or under-predicted in the energy yield assessment process? So that could be things like the gross energy available to the wind plant, largely driven by the wind resource, and then many different loss categories like wake losses or turbine performance losses. But it's difficult to separate or to identify each of these individual loss categories using operational data. So what we have is something called a partial gap analysis that we can perform using OpenOA. So here we've grouped some of the loss categories into buckets. So the first bucket is called turbine ideal energy, and this is estimating the energy that a wind plant could produce if all turbines were operating normally and available all the time. And it inherently includes the wind resource, wake losses, and turbine performance losses. Then there's a method for calculating availability losses in the wind plant and one for estimating electrical losses within the wind plant. And then we acknowledge that there are some other unexplained losses or other environmental losses from icing or other factors that are not captured in these buckets. Okay, now how to run the code. So we start by creating a plant data object, and The first argument we'll pass to this is the analysis type list. These are the analysis methods we want to run, and this just lets the code validate that we have the correct data to run those methods. Then for each of the data types, here I'm using SCADA as an example, we'll specify a pandas data frame or a CSV file name that contains the raw data. And then we have a metadata configuration file. And for each of the data categories, this will allow us to map the column names in the raw files to the internal variable names used in OpenOA. So mapping turbine power production, wind speed, wind direction, and other variables. Actually, before I go to the next slide, next I'll show an example of using some of the utilities toolkits. So we'll look at the filtering toolkit and then power curve fitting. And this will be applied to the 4 turbines from that example NG data set that comes with the software. So first, just looking at the raw data, plotting the power curve for each turbine. Then we apply a window filter, in this case to remove low power production points, a bin filter to remove outliers from the main part of the power curve, and an unresponsive filter to remove periods when we have stuck sensor values. Now, with the cleaned data, then we can fit different power curve models to these points. So IEC, spline, logistic 5 parameter as some examples. All right, for the rest of the presentation, I'll really focus on estimating long-term AEP from operational data. This was the first method developed for OpenOA, the one that's seen the most development effort. But most of the analysis methods run in a similar way to what I'm showing here. So we'll create our Monte Carlo AEP object. The first argument is that plant data object that contains all of our operational data called project. And then we specify different analysis parameters, which reanalysis products we're using, the time resolution, monthly in this case, and the regression model we'll use, linear regression in this case. Then we can plot some of the intermediate steps in the analysis. Here we're plotting the monthly gross energy production of the wind plant determined from operational data against the monthly average wind speeds from our 2 reanalysis products. And we can remove outliers. And then this is used to create a linear regression model that maps the reanalysis wind speeds to monthly gross energy. We then use the linear regression model, apply it to our long-term historical period of reanalysis data to estimate the long-term AEP of the wind plant. We'll run the simulation and then specify the number of simulations, which is the number of Monte Carlo iterations, where we randomly sample different parameter values and quantify the uncertainty in our AEP estimates. Then plotting the resulting AEP distributions. In this case, we're showing the distribution of AEP on the top left, and then availability losses and curtailment losses. And from these distributions, based on the different Monte Carlo iterations, we can quantify uncertainty in our long-term AEP. All right, just showing how these distributions evolve as we run more Monte Carlo iterations. So in this case, after about 1,000 Monte Carlo iterations, the expected AEP and losses and uncertainty start to converge. Now, also showing distributions of different variables or analysis parameters used to estimate long-term AEP. So I won't talk about all of these, but these are values that affect what the resulting AEP is. And then each iteration will get a new value for each of these variables. On the top left is the slope and intercept of our linear regression model. And we get different values because we use bootstrapping to randomly sample different timestamps in our operational data and run the analysis on those timestamps. Metered energy fraction and loss fraction, those are basically noise that we add to the revenue meter and loss measurements to simulate uncertainty in those measurements. Number of years of reanalysis data that's used for the long-term correction. And then reanalysis products. We'll either use MERA2 or ERA5 to quantify uncertainty in the wind resource that's available to the wind plant. So the software development roadmap, the DOE-funded WP3 benchmark project that's been supporting OpenOA since 2018 is actually ending this year. So we'll be looking for new projects to support the code But in the meantime, we plan to maintain the code, and I think this is a good opportunity to collaborate with researchers and industry to keep developing new features. So in the near term this year, we're going to make some improvements to the wake loss method, add hourly reanalysis downloading, continue outreach and promotion. OpenOA was used as part of a We Do Wind challenge. It's an organization that hosts wind energy data analysis challenges where the community can submit their contributions. It was used as part of a YA misalignment challenge for that. Long term, we'd like to expand the analysis methods to meet industry needs, incorporate new data sources beyond CSV files and data frames, perform validation studies for the methods, and then really expand the adoption of OpenOA as a third-party validation tool by doing things like improving the usability and doing these validation studies. Right, and thank you.
Thanks, Eric. Now we'll go to, oh, yeah. You guys are on it.
Do you want to launch the screen share again?
Sorry, just 1 second, won't go into full screen. Okay.
Yeah, so it's me again, Misha. I'm standing in for Genevieve Stark, who is not available today to present on Hercules and WHawk. So Hercules and WHawk are a newer set of tools, maybe the sort of the newest set in our control software stack for running medium and high fidelity time domain simulations of wind plant and wind-based hybrid plant controllers. Okay. Yes. Yeah. So Hercules is the sort of simulation test bed, let's say. So Hercules combines high fidelity wind plant simulations, which are run using AMR Wind, which is again part of the high fidelity WETO code, as well as somewhat simplified models for solar, battery storage, and hydrogen electrolysis. And we're planning to build out more capabilities for hybrid power plants in future. And then Hercules is kind of the glue code that manages all those simulations and allows sort of time syncing between the different let's say assets in a hybrid power plant. To go along with Hercules, we also have the Wind Hybrid Open Controller, or WHawk. This is a separate repository that contains a library of controllers for wind plants and again wind-based hybrid plants to implement real-time controls such as wake steering, active power control for power reference tracking, etc. And also has some sort of, again, simplified versions for simplified controllers that manage battery power production, solar power production. And the idea here is that we can kind of have a hierarchical architecture that lives inside WHawk so that we can have these operational controllers that operate different assets within your hybrid power plant, or purely your wind plant if that's all you're interested in, and then also have supervisory high-level controllers that provide set points to those operational controllers so that we can kind of manage your entire hybrid power plant as a single unit. So the way that Hercules runs is similar in feel to some of our other codes, but because it's kind of managing different simulators, it runs essentially as a sort of a the way that we launch it is through a bash script from the command line. But the Hercules component itself takes an input file that sort of specifies the different assets that you want to run in your hybrid power plant. So yeah, I kind of set we'll point to the AMR Wind input file if you're running AMR Wind for high fidelity wind plant simulations. We'll set the battery size, the solar size, things like that, all within this Hercules input YAML. Again, if you're familiar with YAMLs and their sort of relation to Python dictionaries, then the structure of this will be pretty familiar to you, and it's pretty human readable. So I won't go into too much detail here, but just to point out that that Hercules takes in its input as a YAML again. Next, we have a recording here that Jen made of kind of working through the Hercules kind of workflow. So start with this bash script. This is what will actually be called to run Hercules. Hercules runs using Helix as a message passing interface. So this is a tool for passing messages around different processes that are running different portions of the simulation. And then there are kind of a handful of run scripts that run the different simulation aspects. So it's a bit of a complex system to get everything up and running, but you'll get used to it if you're working with it some. So Hercules run script, the run script that runs either FLORIS or AMR wind, depending on what fidelity you want for your wind plant. And then what we'll just see now is that that Jen is activating the Conda environment and then running the bash script, which kicks off the simulation and then runs through it. Because this is running FLORIS instead of AMR wind for the wind plant, it's quick to run. But if you want to run AMR wind and get high fidelity results, that should also be possible, but that requires significantly more computing power. Then what the outputs are a series of log files that are kind of essentially logs of the outputs in again sort of time domain. So you'll see that there's sort of a bunch of kind of messages, but then the main Hercules output CSV contains the sort of signals for each of the signals that you wanted to record over time. And finally, we have a handful of notebooks that kind of help you visualize it. This is not that well built out yet, but just kind of an example for how you might read in that output file and plot the results that you see there. Ooh. Is that me? I don't know how I did that. Let me see if I can skip forward here. Sorry. Okay, so also an animation of what those outputs might look like in the time domain. So this is for a hybrid power plant trying to track a constant power reference of, I think, 70 megawatts when there's variation in the wind and solar resource. And so there's variation in the power output from wind and solar. And then also a battery that's running to sort of manage that balance and make sure that you can keep hitting that target power output for the plant. So like I said, Hercules and WHawk are quite new for us. And these are sort of in their, sort of initial phase where we're still exploring what capabilities the community is interested in and what, how we should be developing these, how we should be thinking about what fidelity people are interested in, etc. So we're working to build out the control side in WHawk, and that's also in collaboration with Pacific Northwest National Lab. Working on generating good inflow conditions that people can run without having to kind of think too hard about what kind of conditions you need to set up in order to run things, especially with AMR wind, which can be, again, it's a potentially a heavy computational lift. Let's see, and also building out connections with other parts of the WETO ecosystem and especially the Rosco turbine level controller so that we can run farm level controls with WHawk, but let Rosco handle the turbine level operation. Okay, Raf, I think that's me. I want to stop control here and give it back to you.
Okay, great. Thank you everybody for those overviews. And now we'll try it again. We've got another round of polls. Just launch that. Okay, should be another round of polls up. So let me know if you're still seeing the same problem. You can just write in the chat. And we'll give a few minutes to answer these. I know it's a little bit clunky, but just while we, as more people are answering the polls, I want to just share these results here. So here are just the, I think there's 17 responses to this poll. And yeah, I guess I just wanted to share so that we all understand kind of where we are as a community. So especially for these first few questions, have you gotten support in the past? The documentation and examples have been the most utilized resources, closely followed by GitHub discussions and issues. So that's interesting to me to know that all three of these things have been utilized. And then this one I thought was also interesting, that considering things that maybe don't exist or things we could change. As far as user support, the community forums are something that this group, that you all, there's a consensus out that we could use that. So that's really good to know. Someone in a previous workshop had proposed that something like the NREL forums, which historically have been mostly tailored to OpenFast and that collection of tools, that maybe that could be a worthwhile thing to start leveraging more broadly. So that, I think we're maybe hearing that here as well. So thanks for the feedback there. On Hercules, which hybrid energy system components would you most like to see modeled? Battery storage models, clear lead. Which fidelity of computational capability are you most interested in? Mid-fidelity engineering models. So it's also interesting. FLORIS got a nearly 4-star. And FLASC between 3 and 4.
The the FLORIS one was a little weird because tough was on the left for me at least. Like it went from 1 star being tough. I don't know. It's just it swapped.
Oh, is it backwards? Oh, I did it backwards for FLASC.
It was what I would have expected for. Well, I don't know. It depends, I guess. Yeah, they were swapped one way or another. They were not.
I see. Yeah. Good to know. Okay, great. Yeah. Anyway, I think, especially these first two from my side, considering the big picture, I really appreciate this feedback, and this is something that we'll work to take that feedback and find a good way to address that. So thank you. Okay, now I just want to open up the floor. So similar to the previous round of open discussion, considering this group of tools, the wind farm controls and analysis software, I'm curious to hear, what's working, what isn't, what are your thoughts on the learning or onboarding process, and also just generally how well do you understand these tools? And I know it's hard to identify what you don't know, because you oftentimes don't know what you don't know, but if you have any suggestions on maybe what's missing yet as far as capability or the way that we talk about these tools, we'd really like to know that. So what questions do you have here regarding, or feedback regarding these collections of tools? To piggyback on, oh yeah, go ahead. Apurva, go ahead.
Hi, yeah, so I would be a new or a prospective user. So I think what was discussed about in the previous segment of having a starting point. I think having a starting point and a classification of what these different all of these different tools, where they lie in their own specific bins, and where one could start and navigate through. I think that overarching theme of having a roadmap for anyone, whether it's a new user or even an experienced one, I think that would be really helpful. I think for some of the models, it would just be different models can do many things, but then how do I choose between them? Now I have too many options. And of course there are differences, that's why they exist. But how can those differences be highlighted at a much broad level that can help in quickly utilize deciding how we can choose them and then go for it? Which I think some of it does come in with extended use and expertise. That is, it's always fair. And I think something that helps an early identification, that would be really helpful, I guess. Thank you.
Can I follow up with a question there, since this is the second time we've heard it in just 2 questions? Would something like a decision tree be helpful? Of, do you want to model a farm or a turbine? If you're modeling a farm, do you want to model something that varies in time or is steady? Are you working on a laptop or are you working on an HPC? Would those types of questions be kind of what you were looking for to guide you to the right modeling solution?
Am I supposed to answer, or okay?
Well, yeah. Anyway, I saw some thumbs up from Pete and others there. Would that be helpful, Apurva?
I think that would also be really helpful. But if that is, I guess, a bigger effort to put in and develop,
No, not at
then
all.
having a static sort of I'm thinking very basic, a static Microsoft, one of those smart images that just gives a nice visual, and then like, I mean, if you've already said it's not difficult to do a decision tree, then yeah, that interactiveness would definitely be really helpful for sure.
Okay.
Thank
Okay.
you.
Daniel, go ahead.
Thanks, guys. I was just wondering, could you guys, is that NG Open data still available? I just did some Googling there a second ago, and there's a link on like one of the GitHub discussions, but it's no longer active. And I was just wondering if you could share that in the chat. Be interesting to do a little validation testing using that, if that's still available.
I think if you look at, I'll put it in the chat. At least our way of accessing it comes from this particular notebook. So you'll see there's a function at the top for downloading the data.
Awesome. Yeah, that function's probably all I need. Thank you. Thanks for sending that. Appreciate that.
Yeah, no problem.
I'm curious if, based on, or just following on Pete's question earlier in the first section, Misha, if I know Hercules is tailored to specifically the kind of hybrid power plant and controls kind of that specific coupling. But yeah, is there any opportunity, or since it does couple FLORIS and AMR Wind, and it sounds like you're interested in bringing in some more mid-fidelity tools. Yeah, do you think that's meant to be or will be kind of like a general tool to couple, to bring together FLORIS and a higher fidelity tool, or
Yeah. Yeah, I mean, basically, like Hercules, like we said, is kind of this glue code like time simulator thing, and the H is for hybrids, but of course you can sort of switch off everything and just run wind. And we also have support in WHawk for just doing wind control. The long-term vision is that WHawk could also be deployed without Hercules on, a different simulation testbed if you wanted to run, say, with Fast Farm. If we have good Roscoe, if and when we get like good Roscoe connections up and running, then you should be able to run WHawk over Fast Farm, for instance, without necessarily needing Hercules. But even within Hercules, we'd like to have different fidelities available for the wind simulator. So you can choose to run, currently already, you can choose to run a very sort of simple FLORIS stand-in for the wind plant versus AMR Wind, which is obviously high fidelity. And I mean, maybe it can run on a laptop, but realistically, if you want to run a farm of significant size, you're going to need high performance computing for that. But we've actually been talking also about building out, and I think this likely will happen, but just the timeline is a bit up in the air, but building out a kind of a slightly more kind of realistic engineering model stand-in so that maybe you can run sort of initial studies on a sort of a lower fidelity model before you switch over to running on AMR Wind. But so yeah, the hope is that these are kind of modular, and as we build out the capabilities, hopefully we can kind of get to a stage where we can swap out different fidelities, and that WHawk, although at the moment it mostly couples with Hercules, could be run without Hercules over some other test bed if you have it.
Okay. There's maybe a similar but maybe tangential coupling happening in the systems engineering project where WindSC is integrating with FLORIS, but I think that's specific to wind farm layout optimization.
Yeah, right. WindSC is also steady state. I mean, it's running RAND, so also sort of steady state, but it is actually solving, momentum equations and Navier-Stokes equations in steady state. So that's also, another level of fidelity. I think given that Hercules is really targeted at dynamic response, we probably, the mid fidelity thing there will be still dynamic, but maybe sort of based on analytical expressions as opposed to solving Navier-Stokes equations. But hey, you never know. I won't close the door on anything. So yeah, we'll see.
All right, I've got another question for the audience that is maybe tangent. It's not so much about using the tools, but about contributing back. So, and this is, I think, specific to this group of tools because they probably, I think this one more than all the other groups of these workshops actually are more accessible to community development and have gotten quite a bit of community contribution. So for those who have contributed, what's enabled you to contribute back to these open source repositories, or what has prevented you from doing so? And yeah, if you haven't contributed, what's stopping you? Like if you have done your own extension to FLORIS or FLASC or any of these on your end, what are you thinking through when, like, are you just not considering submitting this back to the open source, which is fine, but I'm just curious to know that. And then also, if you are, what are the barriers to entry there? Go ahead, Pete.
So I'd say having it on GitHub makes it easy to contribute back. That's definitely a plus. When teams host their Git repositories on a private GitLab where you need to register for a new account, that hurdle oftentimes is just not worth it, even though it's the tiniest little thing to sign up for a new account. So kudos there. I'm glad NRL's doing that. That's cool. Our team has contributed some small things, but overall, like any of the major extensions we've made to make FLORIS work with our system. Yeah, I don't know if we would be able to retain like any competitive advantage we have if we were to contribute those back. So, whatever little stuff we can help with, like the interface or whatever, happy to contribute that back. But anything around making it work better, I guess, making it faster, I think our executives would have a problem with contributing that back.
Yeah, and that's fair. I guess maybe something that, or I wonder if there's an opportunity for us to kind of try to segment that out to like somehow structure our workflows or even the code itself so that you can make those improvements, but then all the other things that you do that maybe aren't necessarily, that you maybe don't identify as being your competitive advantage, if you could bring that back. I mean, if there's even interest to do that. Do you see any value in contributing back to the open source community? Not on the things that, make your business case, but on the other things.
I definitely philosophically see a lot of value in doing it. I think it's very important, and I think it can be done in a way that doesn't hurt competitive advantage. Maybe just like a side idea that came up now out of this is like more plugin interfaces, so people can build their own sort of extensions, while maybe contributing to the core. I don't know. I know it's like to do something in FLORIS, for example. We've created a subclass of some class inside of FLORIS and extended it. And I guess in our case, now you guys have moved on to FLORIS 4.1. Our subclass probably only works with 2 point whatever. So we're a little stuck there. So a generic plugin interface for any of these tools for people to extend would probably be helpful.
Okay, that's really good feedback. Kind of like the core that takes extensions that plug in. Yeah. For what it's worth, I guess FLORIS was meant to be like that, where you could take specific for wake models, the mathematical formulation for wake models, I think that's maybe enabled, but for lots of other parts of FLORIS, it's not quite there yet. So can think about that there. Yeah, I think as far as the developer communities, I feel like I have kind of a strong desire to make you, Pete, and everybody else, Bart, other people have contributed, to make you feel like you're part of like FLORIS is yours as much as ours, like it is the communities. And so, yeah, if you have any suggestions in that regard, I'm happy to hear that for FLORIS, but also the collection of tools.
Can I pose another question? Oh, I don't know. Before I go ahead.
Anurag, go ahead. Maybe it looks like maybe he dropped Garrett.
Yeah, we're just had some trouble coming off mute. I was going to pose another question to the group. How much is there interest in a multi-fidelity workflow? So as you scale from FLORIS to higher levels of fidelity, this came up a little bit. I think Misha was touching on it. To something like FastFarm or WinDC, and then maybe even up to a higher level LES CFD model. Would fostering that with a common input file or common input format that's easily mapped from one code to another facilitate that? Would that be something that we should invest in? You know, there's a WindIO effort within IEA Wind that is developing this mostly at the FLORIS level of fidelity, and the companion or the comparable tools that are pushed out by some of the other institutions. But we've also considered leveraging that to foster a multi-fidelity workflow. So curious if that would be helpful for the community.
Yeah, that would definitely be useful, I think, to us. I mean, when I look at something like WindSE or Fast.farm, I'm like, okay, I'm starting from zero, basically, if I want to use that. So despite using FLORIS a lot, yeah, I'm going back to square one if I want to jump into these other tools. At least it feels that way. So a converter, common input file, definitely cool.
Appreciate it. Thank you.
Hey, Bart, go ahead.
Yeah, thanks, Rob, and thanks all for the good talks. So I enjoy working with these tools a lot, and I think they're really helpful for me also to push things back to the repositories. If I develop something and push it back, then you kind of take over and keep it up to date and bring it to V4. Saves me a lot of time, saves me a lot of work in the future. Maybe one thing as an additional incentive, and I think it can be really, really small, is maybe more explicitly acknowledge us or the organizations maybe somewhere in the repository. I don't know, let's say someone brings in a big contribution, then if their name comes up in some maybe a community list or something, or I don't know, if you could have a scoreboard, you know, these many lines of code have changed because of these people, but just to really bring it forward, like, oh wow, these people have really, or these organizations have really contributed to the repository, and maybe that's something that we can bring back and say, hey, so some good PR for us to bring to managers.
Okay, that's a really good suggestion. Thanks for that, Bart.
I think this goes also, I mean, very directly to Anurag's question, which he just posted in the chat, which maybe we can all take a second to read. But whether there's any flip side to that, whether there's any potential like sensitivity for your companies, whether you don't necessarily want to be publicly acknowledged, even if you are publicly contributing as an individual kind of contributor. So just maybe something to watch out for, but yeah.
I think quite some companies will be okay sharing that they do use FLORIS. I just think they're often not asked. But I see companies like Vattenfall and RWE talk about FLORIS and FLASC all the time. So I think they would be okay sharing.
Sure. Yeah. Okay.
Yeah, even I saw at a poster at Torque that Wake Adapt is leveraging an in-house FLORIS. So if they're, yeah, that's a good point, Bart. I think maybe we're just not encouraging that that sort of feedback to come back.
Yeah, just to chime in, I think that's a nice idea, Bart. Maybe we can start with a discussion in FLORIS on how to on ideas for how to do this. I'm also, one idea I was thinking, I'm also happy to just have pull requests to FLORIS that are just adding documentation about authorship to different functions and classes. I think we should be very, we should err on the side of making sure we're crediting people for their contributions versus undercrediting. So maybe I'll start that discussion today.
Yeah, I mean, I think this is maybe something also that we can consider for the whole WETO stack. I mean, each tool, each model will have its own perspective on this, but I think generally this is something that we should find a good process for, like a minimum process for, and just try to like let that spread out. So yeah, really good suggestion, Bart. Thanks for that.
And maybe have just one more suggestion to kind of increase engagement. I feel like, again, you guys are doing really, really good work, and then we connect with you on kind of individual basis, just to see how can we steer these tools into something that's more industry relevant, or you know, to be more impactful. I wonder if there's interest to some kind of FLORIS and FLASC forum, maybe potentially when you sketch out your roadmap for the future, just to have people talk about, hey, these are the issues we run into, this is what we would like, this is modifications we've made internally that we're okay talking about, but cannot share the code, or just don't have the resources to make it in a kind of pull request. But that could be fun. Could also be kind of a show and tell. Every couple months, someone just highlights something nice they've done with FLORIS that they are okay with sharing.
So when you say forum, you mean like an online meeting or something, like a live event?
Yeah, exactly. Just with, I don't know if it could be you invite people that have contributed to FLORIS. Yeah, can be anyone that somewhat works with or is on the GitHub.
I like it. We call it FLORIS Live.
I like it. Yeah.
Yeah, I like it too. We've been, especially for FLORIS, we've been trying to move in that direction with our development planning. So we have these project boards and we're doing all this on GitHub, but I don't think it's very accessible if you're not super familiar with GitHub. And if you're not, remembering every day to go check. So in that regard, Bart or anybody else, what's a good way for us to broadcast this out? That there will be a FLORIS that there are updates to FLORIS and kind of more broadly on across this collection of tools, and that, you know, that there will be this forum and that we want you to join. Like, you know, for this, we did all the advertising on LinkedIn, and then I saw that the meeting invites were forwarded around. So there was a lot of word of mouth happening. But more broadly, would you prefer like a monthly newsletter on the WETO tools, or a quarterly newsletter, or is GitHub good enough?
How quickly can you build a poll, Raf?
Yeah, well, seems like it'll only go to half of us anyway. Well, anyway, this is something I'm trying to think through, like what the best way to do this is, especially from this high level perspective, but of the WETO stack, but also particular to the specific models. So if anybody has any suggestions, you can send that to me personally, or any of the model owners directly. We of course want to strike the right balance of giving you information, but not spamming you so that, you know, you just delete the monthly email that comes in.
Maybe just a plug here, just to kind of offer another way of just getting a little more information, is that if you do follow these repositories on GitHub, then when there are new releases, we try to at least spell out, you know, at a high level what changes have been made. So if you want to follow the repositories, you'll at least get those updates.
All right, well, we're coming up on the scheduled time, so I do have another poll. See how it goes. This one's very quick, and hopefully the rating system makes more sense. And then while you rate this workshop, I just want to say thank you to everybody for joining. Like we said a few times, if you have any questions or issues, you can go to GitHub Issues and Discussions to engage with the model owners of all of these tools. And if you have further thoughts on these workshops and how we could do it better, please send it to me directly. I'm also going to send a follow-up email today or tomorrow with the materials from this workshop, and also a link to a feedback form. So if you want to give anonymous feedback, feel free to do it there. And I've listed the repository URLs here just for reference, but I think we probably all know these. And yeah, thanks for your time. This is something that we're really looking forward to doing more regularly. So your engagement here is really helpful and motivating, and also any feedback that you have to make this more worthwhile in the future would really be helpful. So please please share that. And with that, thanks everybody. And there's another workshop on Thursday, or yeah, Thursday. So maybe see you there.
Thanks, Rafael.
Thanks, Ralph.
Yeah, thanks, guys.
Thank you for joining.
Thank you.
Bye-bye.
Thank you.